welcome everyone to lecture 5 of this course on nonlinear and adaptive control. So far we have done two designs, direct model reference adaptive control and indirect model reference adaptive control. I also mentioned that a salient feature of any adaptive controller is that there is an online parameter estimator, which is like a differential equation, which is used to update the parameters of the system or the controller, and that is how the controller is able to adjust its parameters online. So, the direct model reference adaptive control approach involved direct tuning of the controller parameters. So, the online parameter estimator in that case directly adjusted, directly adapted for the controller parameters. In the indirect case, the online parameter estimator estimates the system parameters, and then the system parameters are used to compute the controller parameters using an algebraic relation. So, we almost finished the analysis for indirect MRAC in the last class, but there were some there was just the analysis, the stability analysis which was left unfinished after we modified the update laws. So, in this class we will finish that. Before that, I just want to recap what we had done last time on the indirect MRAC case. Okay, so, what we considered was a plant to the so here we are considering a scalar case, and it is an LTI system. So, it is given by this expression. Here we consider that the parameter b cannot be equal to 0 for the system to maintain controllability. The reference model which the plant wants to follow is given by this expression, and as I mentioned before, this reference model encapsulate the desired behavior that we want from the plant. So, somehow we have the reference model with us, and we want this plant to follow the reference model. So, the objective can be quantified by saying that we want that the plant state x of t should track the reference model state x m of t asymptotically. So, the reference model, as I mentioned before, is a stable one, and the reference signal r of t which drives the reference model is a bounded signal, and as a result the reference model states are always bounded. Okay. So, these are required to set up the problem, and so the indirect MRAC that we had calculated last time, if you recall, is given as a m minus a hat over b hat x plus b m over b hat times r, and this coefficient we refer to as the controller parameter k x hat, and this coefficient we refer to as k r hat. So, notice here that we are looking at a hat and b hat, which are the actual system parameters. So, if say we have the estimates a hat and b hat, we can then using this algebraic relation compute k x hat and k r hat. Okay. So, these update laws for a hat and b hat also we had computed last time, and they are given as gamma a x e b hat dot is given at gamma b u e. This is how the system parameter estimates are updated. Here gamma a and gamma b are some positive adaptation gains, x is the plant state, e is the tracking error, u is the input. So, the problem that we had encountered with these update laws was that b hat could potentially go to 0. So, if that happens, then that creates a problem with our control input, in the sense that if b hat approaches 0, then the control input blows up, which is not a desirable thing to have in your controller. So, what we considered last time was a solution to this problem, which was that if you could somehow project the estimate of b hat to lie in a region which is away from the origin, then maybe we can overcome this problem of the control going unbounded when b hat approaches 0. So, the solution in a nutshell is represented by this. So, say we have, so this is 0 and we know the lower bound on the actual system parameter b. Okay. So, we know that the actual parameter lies in this region. The wiggly lines represent the region where the actual system parameter b lies, and this was what we termed as the forbidden region. So, we do not want b hat to be anywhere inside the forbidden region. As long as it is on the wiggly lines, we are fine with it. So, to make sure that there is this modification to the update law, we use these modified expressions for b hat dot. So, this is I mean all of this we had done last time. So, this is just a recap of that. Okay, so, b hat dot is given by gamma b u e for the case that b the absolute value of b hat is greater than b. It is given by the same gamma b u e. These update laws are dictated by the Lyapunov analysis. So, it stays the same if b hat is on the boundary and the derivative of b hat at the boundary points in the region which is outside the forbidden region. That means, in the region where we have these wiggly lines. So, which is given by this expression. So, this just represents that the derivative of b hat points in the direction outside away from the forbidden region. So, if that happens, we continue to follow this update law. Otherwise, we say that b hat dot is equal to 0, which means that b hat retains the value that it had previously, and we continue evaluating for these conditions, and based on where b hat is, we apply b hat dot cases. So, this is case 1, this is case 2, and this is case 3. Case 1 and case 2, we basically apply the same update law that came out from the Lyapunov analysis, and for case 3, when b hat lies on the boundary and the derivative is pointing inside the forbidden region, that is when we stop the updation of b hat. Okay. So, this ensures that if we select the initial estimate to be greater than b lower bar, then for all time we can say that b hat of t is greater than equal to b lower bar. This is for all time. So, these update expressions make sure that if initially we select the estimate of b hat in the region where we have wiggly lines, then for all future time it stays there. and it does not come inside the forbidden region, which is what we had desired. Okay. So, so for the indirect MRAC case, we can say that we require the lower bound on B and the sign of B. So, this is slightly different from the direct case, where we had only required that the sign of B was known. In this case, in addition to the sign of B, we also require that the lower bound on the actual parameter B be also known. Okay. What we had not done last time was that with this modification, do we get a stable controller. So, stabilizing control system. So, that is something that we will be doing in this lecture. So, let us consider the same Lyapunov function candidate that we had considered last time, which is half E square plus half gamma A tilde square plus half gamma B tilde square. All right. So, this is a positive definite radially unbounded decrescent Lyapunov function candidate. So, we take the time derivative and then substitute for the open loop the closed loop error system. Oh, so yeah, that's fine. Okay, now if we substitute for the expressions for A hat dot and B hat dot that I had just mentioned, then what we get is 3 cases, because for B hat dot we have 3 cases. So, for cases 1 and 2, we see here that we use the same expressions for B hat dot. So, we get V dot to be equal to A m E squared. This is what we had gotten last time. So, there is no change. So, the change is in case 3. So, for case 3, where we had actually modified the update law to B hat dot equal to 0, we get a different expression for V dot. So, let us calculate what we get. So, if you substitute for, so we basically have to substitute for B hat dot equal to 0 here, and what we end up with is A m E square plus B tilde E u. So, this is what you will get when you do the case 3, we get an extra term. So, if you look at cases 1 and 2, we get V dot to be negative semi definite, and so the stability of the equilibrium point is assured. For case 3, we need to figure out if V dot is negative semi definite. So, A m E square we know is a negative term, but B tilde E u is the term that we would like to know the sign of. So, it is not apparent what this sign would be, but let us look at what case 3 is actually. So, what is case 3? So, let us go back and look at the conditions for case 3. So, case 3 is this condition where let us just write it down. So, case 3 is when B hat is on the boundary, that means B hat the absolute value of B hat is equal to B lower bar, and the derivative is pointing inside the forbidden region, and in that case is when u e signum of B is less than 0. Okay. So, using this information and the fact that b hat dot equal to 0, let us see what we get. So, we get v dot to be equal to this, and now the task is to figure out the sign for this term b tilde e u. So, we can rewrite this term as b tilde signum of b times e u signum of b. So, I have just multiplied this expression by signum of b square, which is equal to 1. So, it does not really affect anything, but it will help us figuring out the sign of this term. So, we know that E u signum of b is less than 0, because that is case 3. What about this expression b tilde signum of b? So, b tilde signum of b is b minus b hat signum of b. So, let us consider the two cases when the first case is when b is positive. So, then sign of b is greater than 0, and b minus b hat is also positive. So, this unless b hat becomes equal to b. So, in that case it will be 0. So, this expression will be greater than equal to 0 for the case when b is greater than 0. Let us consider the case when the parameter b is negative. So, in that case signum of b will be minus 1, and b minus b hat would also be negative, and so this entire expression would again be greater than equal to 0. So, we can safely say that this is greater than equal to 0, and these two combined would give you something which is less than equal to 0. Okay. So, what we can say from here is that b tilde e u is always less than equal to 0. So, then let us look back again at v dot. So, v dot is given by a m e square plus b tilde e u, and we know that b tilde e u is less than equal to 0 and a m e square is less than 0. So, we can say that v dot is less than equal to a m e square, which still makes this v dot as negative semi definite. And so, what we can conclude from here is that the same properties hold that we had for the case where we had used unmodified update laws. For the case where we projected the estimates to lie in a region which is away from the origin, what we see is that we again get v dot to be negative semi definite, which means that the equilibrium point is Lyapunov stable, and all the signals are bounded. Using Bartlett's lemma, again we can prove that the tracking error converges to 0. So, the stability properties are preserved even in the case of projection modification of the update loss, right. So, even with this modification, we are able to prove that the system is Lyapunov stable. So, in both the cases, direct and indirect, we have been able to show that we get stability. So, for the indirect case, if we have to implement, then we can look at a block diagram for that case. So, we have a plant x dot equals say x plus b u with an input u and an output x. There is a reference model. This is the plant. This is the reference model, which is the desired behavior that we want from the plant. So, this is given by a m x m plus b m r. This is driven by the reference signal r, and output is x m. All right. So, what controller have we used here? We have used a state feedback controller with dynamic gains. So, u is given by k x hat x plus k r hat r, and these expressions for k x hat and k r hat are obtained from the update laws of the system parameter estimates a hat and b hat. So, we have an online So, we have a hat dot equals whatever we had done found, and b hat dot as the projection modified update laws. So, these are the online system parameter estimator. Okay. And the input to this block is the control input u, the state x, and the tracking error e. So, which is just the difference between the plant state and the state of the reference model. Okay. And what we get is a hat and b hat as the output, which are the estimates of the system parameters. These are then used to compute the controller parameters k x hat and k r hat. So, that expression we have mentioned to be this and this. So, once we know a hat and b hat, we can evaluate k x hat and k r hat, and that is then used to update the controller. So, the input to the controller is x and r. Okay, so this is in fact connected. Okay, yeah. So this looks fine. Okay, so we have seen the two cases, direct MRAC and indirect MRAC, and we have considered the plant to be unknown. So, system parameters a and b are unknown. The plant is parametrically uncertain, and we have been able to design an adaptive controller to track a reference model, and we have actually shown that the equilibrium point is stable. Further, we have also shown that the tracking error is convergent. So, as for the difference between the direct and the indirect approach, there is no general guideline as to which one is better. It depends on what your application is. In certain cases, direct may be more suited. For example, for the indirect case, we have an extra step where we compute the controller parameters using an algebraic relation. So, so this step can get computationally expensive for large dimensional systems. So, in that case, the direct approach may be more beneficial, because you directly compute the controller parameter, the k x hat and k r hat. However, in certain cases where you benefit from knowing the estimates of the system parameters a hat and b hat, it might be better to use the indirect approach. So, there is no general guideline as such, it varies from case to case. All right. So, now we move to the case where we have more than one state. So, we considered a scalar example which was illustrated the mechanics of how to design these adaptive controllers. It becomes slightly more complicated if we consider the vector case. So, I am going to do the direct MRAC for the vector case. Okay. So, we consider the plant to be A x plus B u. So, x is n dimensional and u is m dimensional, which means that the matrix A is n cross n and B is n cross m. The reference model similarly is given by x m dot equals a m x m plus b m r. So, again x m is n dimensional, r is m dimensional, and a m comes n cross n and b m comes n cross m. And again r of t is a bounded signal, which means that the reference model state x m of t is also bounded. Okay. So, we have set up the problem. The objective again is to track the state of the reference model. So, the control objective is stated as x of t tracking x m of t. So, although the mechanics here is similar to what we had done for the direct case, direct scalar case, but there are some subtle aspects which I want you to be exposed to, and that is why I am doing this again for the vector case. Also note that here in all the cases that we have done so far, we assume that the states are available for measurement. So, that means that there are sensors available to measure the entire state vector x. The problem becomes more involved, more complicated when we say that we could only measure the output y, which may not be the entire state vector. Okay. So, let us continue with this problem. So, the tracking error E of t is defined as x of t minus x m of t, and the error, the open loop error dynamics, is given by differentiating the tracking error. Okay. And the controller u, similar to the scalar case, is given by k x hat x plus k r hat r. So, it is a state feedback controller where k x hat and k r hat are time varying gains. So, notice here that the dimension of k x hat is given by m cross n matrix, and k r hat is also a matrix. In fact, this is a square matrix by m cross m. Okay. So, here the control gains are in fact control the control parameters and in fact matrices. Let us see how that changes the entire analysis. Okay, so once we substitute this u in our open loop error system, we get the closed loop error system. So, the closed loop error system is given by substituting u in the expression for the open loop error system, and what we get is a plus b k x hat x minus a m x m plus b k x hat r minus b m r. All right. So, again we consider that that there exists ideal gains k x and k r such that a plus b k x is equal to a m and b k r is equal to b m. So, these are the matching conditions. In the vector, in the scalar case, the matching conditions can be computed trivially, and they exist for all values of a, b, a m, b m. But in the vector case, as you can see, since a, b, a m, b m are matrices, it may not be possible to always find k x and k r which satisfy the matching condition. So, in this case, we this matching condition assumption becomes very crucial, and okay. So, once we assume that the matching conditions are true, instead of using k x and k r, we use k x hat and k r hat, because we do not know the actual system matrices A and B. So, it is not possible to compute k x and k r beforehand. So, using these matching conditions in the closed loop error system and doing some manipulation like we did for the scalar case, what we get is E dot is equal to A m E minus b k x hat minus. So, this is what we get, where k x tilde is defined as k x minus k x hat, and k r tilde is defined as k r minus k r hat. So, these k x tilde and k r tilde are the parameter estimation errors, in this case controller parameter estimation errors. So, now we have got this closed loop error system, and we need to analyze the stability of the overall system consisting of the tracking error as well as the parameter estimation error. So, we consider Lyapunov function candidate similar to what we had done for the scalar case. Here there are some differences. So, V is a function of E and the other error states. So, one way to choose the Lyapunov function candidate in this case is E transpose P E plus trace of k x tilde transpose gamma x inverse k x tilde plus transpose gamma r inverse k r tilde. Okay. So, here P is the positive definite symmetric solution of the Lyapunov equation. So, what I forgot was that here A m is Hurwitz. Okay. So, it is a stable reference model. Okay. So, P satisfies this Lyapunov equation. P is positive definite and symmetric, and Q is also positive definite and symmetric. Okay. And TR represents the trace operator. It denotes the trace operator, which is the trace of a square matrix. And it is given by the sum of the entries on the main diagonal. Now, why we have chosen the Lyapunov function candidate in this way? One reason that you could think of is that we want to choose a positive definite function, and the first attempt that we want to make is to choose a sum of squares. So, in the scalar case, we had chosen the first term as half E square. Since E is a vector here, we choose it to be half E transpose P E, and it just becomes more elegant if we use P, as we will see later. The expression 2 and expression 3 are positive definite expressions. So, you can prove that this expression inside this trace expression involving k x tilde and k r tilde are in fact positive definite. So, we want to choose some positive definite term involving the parameter estimation errors, and since these are matrices and V is a scalar, we want to come up with a term which is positive definite, but at the same time it is a scalar term. So, this trace operator is very useful in this scenario. In fact, it has very useful properties which we will be exploiting. So, trace is actually a linear operator, and some of the properties that we will be exploiting are the trace of two square matrices A and B is given by so sum of these is given by the individual sums of the traces. The trace of alpha times A is given by alpha trace of A, where alpha is a scalar. Trace of A is equal to trace of A transpose, and a very important property that we will be using is the product of two matrices which are compatible dimensionally. So, say A is n cross m and B is m cross n, then trace of A B is given by trace of is equal to trace of B A, where B we know that is m cross n and A is n cross m. So, the entire the product becomes m cross m. Okay. So, this is an important property that we will be utilizing. Okay. So, this Lyapunov function, let's go back to the Lyapunov function. I just mentioned that this Lyapunov function is positive definite, it is also radially unbounded and decrescent. So, why we worry about decrescence here is because the closed loop system involving the tracking error E and the dynamics of k x tilde and k r tilde is in fact non-autonomous because of this reference signal R on the right hand side, which is time varying. So, if we want to use the Lyapunov theorems that we did in the previous lecture, then we should talk about decrescence if we are to conclude uniform stability. Okay. So, let us take the time derivative of v. So, taking the time derivative, v dot is given by E transpose E dot trans E plus half E transpose P E dot plus trace of k x tilde dot transpose gamma x inverse k x tilde plus tilde transpose gamma k x tilde dot plus half trace of k r tilde So, by now you should be comfortable with the Lyapunov analysis and the fact that the analysis can actually help you construct the controller. It is not just an analysis tool, but it is also a design tool. Okay, so then we go ahead and substitute for E dot from the closed loop error equation. So, this becomes so E dot transpose. So, we have to take the transpose of that expression. R transpose K R transpose plus half AME so just a minute. E transpose P E dot okay plus now if you look at these two expressions and use the property that transpose of a matrix is equal to the transpose trace of a matrix is equal to the trace of its transpose, we can exploit that to get the expression as trace of k x tilde transpose gamma x inverse k x hat dot plus trace of k r tilde transpose gamma r inverse k r hat dot. So, we have taken the derivative of k x tilde and k r tilde and this is what we get. Okay. So, let us cancel common terms and after some manipulations what we get is half P transpose P A M plus A M transpose P times E, and then the rest of the terms. Okay. So, the first term in the expression for V dot is this one. So, we know that P A M plus A M transpose P is equal to minus Q, right. So, this is what we had assumed here, that P is a solution of this Lyapunov equation, and so we can replace this by minus Q, where Q is positive definite, and so the first term in fact becomes negative. Let us look at the other terms. Now, we want to choose the update laws for k x hat and k r hat in such a way that we cancel the other terms in the expression for V dot, because those terms are sign indeterminate. We do not know what their signs are. So, it is better to cancel them using these update laws. The only challenge here is that with the trace operator, how do we come up with the update laws for k x hat and k r hat. In fact, the trace operator will help us choose the update laws. So, if you look at this expression, let us just simplify this expression to make our life easier. So, what we get here is minus, so this is minus E transpose P, and let us get rid of the bracket here, B x minus okay. So, now it becomes easier. So, we have k x tilde transpose here, and we want to choose k x hat dot and k r hat dot, and we want to cancel these two terms. So, if you look carefully and choose k x hat dot to be minus gamma x B transpose P E x transpose, and k r hat dot to be B transpose P E r transpose. So, if we choose the update laws like that, then we will see how they are going to help us complete this analysis. So, the first term is E transpose Q E. So, we do not have a problem with this term because this is a negative term, and then we have minus E transpose P P x tilde x minus E transpose P B k r tilde r minus trace of k x tilde transpose gamma x inverse k x hat dot. So, which is what we get is the positive sign here. Okay, gamma x B transpose P E x transpose plus So it still looks a little difficult to convert it in the form such that we can cancel these two terms, but if you use the property of trace, we see that it is doable. So, one thing that we can do is to take the transpose of these terms, that will make life easier for us. So, let us do that. So, these Lyapunov analyses typically run into pages. So, you have to be patient with it. R transpose K R tilde transpose B transpose, since P is symmetric. So, this is it. Then we have plus trace So, these update laws are strategically chosen to cancel these terms. So, they have not come out of thin air. So, now it looks like we can do something about it. So, if you consider this to be a matrix and this to be another one, similarly here if you consider this to be one matrix and this to be the other matrix, then we can use the product rule, which is the trace of the product of two compatible matrices is equal to the trace of the matrices taken in the opposite order. So, we can write this term as trace of k x transpose k x tilde transpose B transpose P E, and this term we can write as R transpose K R transpose B transpose P E. Okay. So, now it looks like at least the argument of the trace is similar to is in fact same as the other terms, but how do we cancel it, because now we have a trace operator in these two terms. So, what we if you find out the dimension of the argument matrix, you find that in both the cases these two are in fact scalar expressions. So, these are scalars, and trace of a scalar is simply the scalar itself. So, this is further equal to x transpose k x tilde transpose. So, we remove the trace from this expression, and this one also becomes R transpose K R tilde transpose B transpose P E. So, now we can cancel this with this term and this with this term. So, finally, we end up with V dot equal to minus half E transpose P Q E. So, this is negative semi definite, and so the equilibrium point is Lyapunov stable. So, we can further say that since V is positive definite and V dot is negative semi definite, we can V dot is less than equal to 0, we can say that V is bounded, which means that the tracking error. So, you have to look at the expression for V. So, V being bounded means that E has to be bounded and k x tilde has to be bounded and k r tilde also has to be bounded. So, you have to be very rigorous about it. So, E of t, k x tilde of t k r tilde of t are all bounded, and since x m, which is the state of the reference model, and k x and k r are all bounded quantities, what we can further say is that x of t, k x hat of t, k r hat of t are also bounded. So, have we proved that all signals are bounded? No, we still need to prove that the control input is bounded. So, if we go back and look at what the control input is, we find that it is k x hat, which we have proved to be bounded, times x, which we have proved to be bounded. K r hat is also bounded, and r is bounded because it is the it is given to be bounded. So, we can conclude from here that u of t is bounded, which is an important statement to make. Okay. So, in this case we have considered that A is unknown, however, B is considered to be known, right. So, how do we say that A is unknown and B is known? Because the controller does not require any information about A. If you look at the controller u, it is given by this expression, and then let us look at how k x hat and k r hat are generated. So, let us look at the update laws, and we find that these update laws do not contain A. So, this design does not assume any information about the matrix A. However, you can see that this design still needs the matrix B. So, that is something that we have to assume, that we know the B matrix. If you try and do the case where B is also unknown, you might end up with a local result. So, that is something that you could try on your own. This is a global uniform global asymptotic, this is not an asymptotic result, but uniform global stability. The case where B, A and B are unknown is something that you can try on your own. You can also try the indirect MRAC, the vector case. Okay. So, in this lecture we have covered the general problem of direct MRAC, and we also finished the analysis for the indirect MRAC for the scalar case. Hopefully, this has given you enough information about how to design model reference adaptive controllers. So, in the next class we will continue, and so we will do the case where we have some uncertainty in the system dynamics. Okay, thank you.